It's a pleasure to welcome David Stork today from Rambus Labs, who's got some really exciting work that I heard about this summer at a talk he gave in Barcelona about lensless ultra-miniature imagers. He recently joined Rambus Labs, having been at Ricoh before that. He's done all kinds of interesting things. You may know the book on pattern classification by Duda, Hart, and Stork. And he also has another whole career using computer vision techniques to analyze art, which I don't think he's going to talk about today, but that's another interesting facet. And thank you very much for coming. We're really looking forward to your talk, David.
Thank you very, very much. Thank you, everyone, for coming. Today, I'd like to talk about lensless ultra-miniature CMOS computational imagers and sensors. And when I say ultra-miniature, what do I mean? Well, here is the Medegus endoscope camera. It's about 1 millimeter across. It's one of the smallest commercially available imagers you can make, but the size is limited by the need for lenses. You have a converging lens on the front of it, and having to have the size of the lens and the air gap leads to this, the size being limited to about something like that. We've figured a way to take some of the burden of focusing and putting it in computation, taking it away from a lens and putting it in software, if you will. And this permits a new class of lensless imagers. We call them PicoCams, much smaller than traditional focusing systems. How small? Well, here's a penny again. And here's one of our PicoCam imagers. You can fit 8 of them in the 0 of the 2009. Here, for a better comparison, is a diameter of a human hair. There's 10 microns. Here is the phase grading, I'll explain it in a moment, of our PicoCam imager, roughly 80 microns across. This one is roughly the diameter of a human hair. The data I'll show you is for one about twice that size, twice the diameter of a human hair. And so here's a phase grading just to show you a micrograph of part of our imager. But how do you make such an imager? It doesn't look like a standard camera whatsoever. Before I get to that, let me put this in the grand sweep of the development of imaging. I think we're in the midst of the 4th major revolution in imaging. If you stand back and look at the grand sweep of the development of optical imaging, the first major revolution was in the 13th century, where they developed converging lenses and curved mirrors so that you could project an image. And of course, that led to microscopes and telescopes and a lot of optical devices. The second major revolution was chemical fixation in daguerreotypes and photography and so forth at the beginning of the 19th century. But the third major revolution came from the confluence of optics, the development of optics, and the digital realm of signal theory, information theory, computation, theory of computer science, and the hardware that goes along with it, CCD arrays. And that revolution is, of course, the digital imaging revolution. Everyone's with their iPhones and mobile phones and stuff like this. It's pretty much replaced film everywhere. Well, the 4th major revolution came from the confluence, the deep integration of the optical and the digital. We call it digital optical imaging or computational imaging. And this is where you don't capture an image the way we have for millennia, really, but instead we compute an image. The optics can be radically different, not like your standard lenses, but we're going to capture signals that won't look like an image at all, but the signals will contain enough information that we can sense it and then compute the image. Well, I'd also like to put our PicoCam in another context, and that is the size of other imagers. Here's a graph of the spatial volume, the physical volume in cubic millimeters of different types of imagers. And here's the resolution in pixels of a single frame of that. So this ranges over 20 orders of magnitude. You might not be able to read, but this is a log-log scale, 10 to the minus 9th here and 10 to the 11th here. The largest imager in the world is the Grand Canary telescope. It's a humongous telescope. The second largest is the Hubble Space Telescope and so forth. This has a very large resolution, number of pixels, and so forth. And you keep going down here. Professional cameras, the iPhone camera is this one, and the Medegus one I showed you is right here. Way down here is a single unlensed bare naked photodetector. It has a resolution of 1 pixel, and it's roughly 10 to the minus 9th cubic millimeters. What you notice, however, is that there's a 7 order of magnitude range of physical volumes, of physical sizes, where there are no cameras. You cannot make them. Why? Because the constraints of having a lens, or curved mirror, but mainly lens, tops out or bottoms out right around here, and you can't squeeze things smaller and push them closer together. So we want to fill this valley of darkness, and the PicoCams that I'm going to be talking about all lie in this region. They're smaller than any other imager that's ever been made. Now, why would a company like Rambus or any company be interested in this? That comes from looking at this blue curve. This blue curve is the sales in units per year of the different imagers of different sizes. So if the Grand Canary telescope is about 35 years old, so you sell 1/35 of those per year along a log-log scale. Hubble telescope is 25 years old, and so forth. The iPhone sells 2 billion, and so forth. But what you see is there's this dramatic drop-off. There's just nothing. Nothing's being sold here. And you have to think about the customer interest. Are they saying, you know, we only want imagers down to here, and it just happens to be the size that lenses provide a limit to? I think probably not. That there are lots of applications down here, many that we don't even know about yet, that once we have imagers that size, we'll be able to satisfy. Now, this is the graph of the sales in 2012. I don't have all the data, but roughly, if you were to plot this blue curve in sale units per year, also a log scale. In 1970, it might have looked something like this, 1980 like this, 1990 like this, and so forth. We're selling more and more imagers all the time each year, per year. But you would also notice that the peak starts getting at smaller and smaller imagers, that the peak of sales keeps getting to smaller and smaller imagers, like the iPhone is one of the best-selling cameras on the planet, 2 billion per year, and so that keeps getting smaller. So you have to think of this blue curve as a tsunami, a wave of customer demand that's flowing to those smaller and smaller images and hitting a brick wall and just stop because of physical limitations due to the need for the use of lenses. And what we're trying to do is break this wall and let all that customer demand flow into the valley of darkness. One of the other trends that supports computational imaging is the following. If you look at the development of cost, the cost of optics for a large number of optical systems decreases at about 5% per year. Yes, if you buy a high-end Nikon camera lens, its cost is actually going up every year, but that's not the overall average. If you look at most lenses, the cost drops at about 5% per year. It has a lot to do with the cost of oil, it turns out, for plastics. But if you look at the cost of computation per time, it's dropping precipitously by Moore's law. So if we can develop imagers that rely on computation, even if they're expensive now, even if they use a lot of computation now, wait a while, and that's going to drop off much, much faster than will the cost of optics. And that's exactly what our computational imagers do. We do a lot of computation in order to compute our image. So now to the physics. For hundreds of years, the way we make imagers has relied on either reflection. You have a curved mirror, as in a reflecting telescope, or refraction, the bending of light as it goes through a lens for a camera. But just last year, 2012, my colleague, Patrick Gill, and his colleagues then at Cornell University, used instead the physical principle of diffraction, the wave interference of light, in order to make a camera on a chip. It was the planar Fourier capture array, and I'll describe that in a moment. But our system is the PicoCam, which is related to the planar Fourier capture array tenuously, but extends beyond it in a number of ways. And so instead of using reflection and refraction, we're using diffraction. Well, let's remind ourselves about the sort of underlying algorithmics of image capture. If you have a standard lens, and we look at light coming from different angles, like a distant star, plane waves coming, the lens collects all the light and brings it to a focus at a given point here. So as a function of position along the sensor, we have a delta function. All the collection of the light comes due to the lens. And you don't need much computation to get the image. You just read out the pixel values here, and you got your image. If instead you use diffraction, use a diffractive grading, that is like has very fine structural patterns on it, so that light, as it passes through diffraction, you can get light coming for a single pixel back here. If light comes from this direction, it will strike the pixel. If light comes from this direction, it will strike the pixel, and so forth, but not from here. So the response function is not a delta function. Instead, it has some, in this case, repeated pattern like this. Well, that doesn't give you an image, but it contains the information that will allow us to compute an image, as I'll get to. So here is how the planar Fourier capture array works. This is a cross-section of a computer chip, silicon chip. This bar says 10 microns here. And the cleverness of that group was thinking of the standard CMOS process, VLSI process, and the wires you have in it, and said, we're not going to use these wires to conduct electricity. Instead, we're going to use them to make a diffraction grating. So here is metal 6, one of the layers of the metal. And we're looking end on, so every one of these black dots, I hope you can see, is a wire going back into the plane here. And there's another grating down here, also made of wires. And I hope you can see it here, but this is a simulation, a full EM, magnetic simulation of the energy density. For light coming in this direction, there'll be places where it interferes and has more energy density, that's brighter yellowish, and then places where it doesn't. Constructive and destructive interference for you physicists here. And then if you look at any one of these individual pixels here, it will have a particular signal. If light comes from some directions, this will get a lot of signal, but not from others. From one, it does, and not from others. Each one of these pixels could have a slightly different response. And one way to think about that is imagine you're the pixel lying on your back, really, really teeny. You're lying on your back, looking up at those wires. Here are the wires in layer 6, and you just see, clear black wire, clear black wire, clear black wire. And now when we put the other layer of wires in that happens to be closer, that's something like this. And you can see it's like picket fences, 2 picket fences with their slats either aligning or not aligning. So light from this region will get through and lead to a signal in you, the photodetector. Light from here won't. Light from here will. And so the response function will look something like this. Yes, I'm responsive. No, I'm not. Yes, I am. No, I'm not. This is this repeated pattern that I showed you just a moment ago. And here is a simulation. I hope you see these arrows are changing as the angle of incident light comes through these 2 wire gratings. And this is a full EM simulation of the electric field density inside the chip. And if you had a single pixel down here, it would have this response. For one angle, nothing, then a lot, nothing, a lot, as a function of angle of the incident. And so we can take a chip. There are bars here for the wires at different orientations. Some of them are vertical, some of them are tipped 10 degrees, 20 degrees, and so forth. And also different spatial frequency, different wideness, separations, in order to capture different Fourier components of the visual field. And then you can take those and put those together computationally, and I'll come back to that in a moment, to create an image from the source. So here are the so-called basis set. For the planar Fourier capture array, one of the gratings is vertical and has this thing, and another one's tipped and so forth. And these are the responses. So each one of these little boxes represents a picture of the world that will lead to a large signal in it. So this one says, if light's coming from here, I'll get a signal, not from here, yes from here, not from here, and so forth. And then at different orientations and different separations. Now, this is completely arbitrary. I can put these anywhere I want, and it makes no difference. However, I arrange them this way to show that they are grouped in sets of 4. If you know Fourier analysis, you need at least 2 independent measurements to get the amplitude and the phase of one of these gratings. They used 4 just to reduce the noise or the possible error. And so each one of these is shifted. This one is in a given phase. This one is shifted by 1/4 of 2 pi and 2/4 and 3/4 of 2 pi, or 360 degrees in phase. And capturing all those numbers gives you the amplitude and the phase of this spatial frequency, visual spatial frequency, and that orientation. And likewise for all of those. So that's how you capture the information about the world and you put it together. All right, well, that's the planar Fourier capture array, but there are a number of problems with it. Number one, it's not very light sensitive. Each one of those amplitude, we call it an amplitude grading because it affects the amplitude of the light passing through, cuts out roughly half of the light. So one cuts out half the light, the other cuts out another half, so you're only getting 25% of the total light getting through. That's bad news. You're losing signal. Moreover, and this was a subtle case, a subtle issue, but it turns out to be extraordinarily important. When you manufacture these kinds of chips, you cannot, the people who make chips, the Intels of the world, the Hynix, all these companies, really don't care. They don't spend time trying to make sure that the thickness of their chip is exactly right. They're not doing optics. They just care that the electricity gets through. So when you make it, sometimes it'll come out this separation. Sometimes it'll come out this separation. Sometimes this separation. And they don't care. But we optics people really care because the separation between these two will lead to very different signals. So one way around that is our PicoCam phase grading. Instead of using an amplitude grading, I hope you can see it here, but here you have this silicate, just the standard CMOS glass, really. And it's a little bit thicker here, thinner, thicker, thinner, thicker, thinner. And this introduces a phase delay in the light, which can act very much like an amplitude grading. And it also allows much more of the light to come through. But what about that problem of the separation between the grading and the sensors? Well, here was sort of our cleverness, Patrick's and mainly his cleverness, was finding a mathematical form of the phase grading that leads to the pattern of light on the sensors being independent of the manufacturing defects. If we design it like this and the manufacturer makes it this thick, no problem. How does that work? We get what are called curtains, regions that very low energy density, the destructive interference, that the light cancels itself out in these long bars like this. If you go back to the earlier ones with the picket fence structures, it gets bright, dark, bright, dark, bright, dark as you go along. Here it's just dark, 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 all the way down. And how do we do that? And here was sort of the core mathematical idea that allows you to do it. Here's a cross-section of the phase grading. So it's thick here, thin here, thick here, thin here. Let's look at the line along the middle. This will be one of those curtains. We've designed it such that for any point to the left of this dotted red line, wherever it's high, the phase grading is high, it has a corresponding part that's low here. This thickness corresponds to 1/2 wavelength difference for the light that's coming in, and therefore, any light that comes from a point here reaches X will be canceled by light that comes from here to that point. It's the same physical distance it has to travel, but one has a phase delay of pi radians, and so it's destructive interference. Likewise, from this point here and its corresponding point, a high on this side, low on this side, cancels out. Notice the cleverness here, that it didn't matter where vertically I had to put that X. If I did it down here, I would still get cancellation from this point and this point. Anywhere along this. This is the core reason we get a curtain along this if we have a phase anti-symmetric grading. That means that the phase on one side is opposite from the phase on the other by 2 pi, by pi, 1/2 wavelength. And you can do other shapes, but if we're just going to use binary phase gratings, just 2 levels, if you will, it makes manufacturing simpler, and you can still get all the properties we need. So this is the core optical property of our PicoCams, this phase anti-symmetric grading. Now you see it here in a one-dimensional slice, but of course if we want to make an imager, we're going to have to get information vertically, horizontally, and all possible orientations. So a 1D phase grading won't work. We need to somehow generalize that to 2 dimensions. How do we quick question?
Or do the wavelengths like between red and
There will be a very slight difference if we choose. I have a slide on that. That's an excellent question to anticipate. If we do it just as I've said, there will be a difference between red and blue, but if we have yet another layer that has a different index of refraction and different dispersion or Abbe number, we can cancel those off, and I'll show that in a slide, about 3 slides, that shows that it's almost pi over 2 pi.
So why do you want those curtains? I mean, is that going to correspond to a pixel or something?
Well, you can make it onto a pixel. It means that when you have your whatever pattern of intensity you get for the light coming in, it's independent of manufacturing variation.
Okay.
So here is a different graph. It's kind of complicated, but stick with me. Here is the response in a single pixel in one of those planar Fourier capture arrays as a function of azimuthal angle, the light coming in from this direction, this direction, this direction, minus 40 degrees, minus 10, 0, and so forth, for 400 nanometer light. We will get that oscillatory structure that we saw before. It goes up, down, up, down, up, down, up, down, like this, that I demonstrated before in that little animation and so forth. But indeed, as this question suggests, if I use a different wavelength, it does not stay the same as a function of wavelength. If I go to a different wavelength, it'll be high, low, high, low, high, low. So not only is the planar Fourier capture array variant to manufacturing distances, it's variant to wavelength, and we don't want that. We want a panchromatic imager, one that will give us a black and white image no matter what wavelength is used. Here's the same simulation, same structure, for our phase anti-symmetric grading. Again, azimuth angle, the light coming in at different angles. And you take blue light, for instance, and we get this kind of oscillatory structure, fine. But notice how it doesn't depend very much at all on the wavelength. If it's high for blue here, then it's high for green, and so forth, high even for red. In fact, this one happened to be optimized for blue, which is the worst case. You would optimize it for the green right in the middle, and that way the total variation difference between the red and the blue would be as small as possible. So it's much more invariant here than over here. Now so you see these troughs here. These are not the curtains. Right? This is a graph. This is not a picture inside a slice of the silicon. It's just saying, as a function of wavelength, your response does not change. And that's just what we want. And that phase anti-symmetric grading ensures it. In fact, Patrick proved that if you want that property, the manufacturing invariance and wavelength invariance, to create these curtains, the only function that will satisfy that, the only one, is a phase anti-symmetric grading. Okay, so again, we use our phase anti-symmetric gradings, and so we have several degrees of freedom. So long as we keep this phase anti-symmetry, we could choose the widths of them with some freedom. And depending upon the wavelength we're interested in, or more importantly, the scale, we can make these very, very complicated, very, very simple, so long as they have this phase anti-symmetric property. But again, this is a one-dimensional phase grading. We need to do it in 2 dimensions. So here is that graph as a function of wavelength, whether it's it should be pi phase difference all the way through. This is if you just use one material, a particular kind of silicate glass. The details aren't important. It's almost invariant, but if you use 2, I'm sorry I lost it on the deck. I don't have, but the graph looks something like this. Very close to pi throughout. Not exactly, but much, much better. Way, way better than the planar Fourier capture array. But again, we start with this linear grading, but we now need to sample the visual field in different orientations. There are a number of ways you could do that. The first would be to take one of these gratings and just sweep out different angles, make a bullseye, if you will. So any slice along here has this kind of structure, and that, now we've got one at horizontal and 10 degrees, 20 degrees, and so forth. But there are problems with this involving repetitions and cycles. The details are kind of not worth our time, but there's some problems with this. You could also take a grating and just sort of sweep it radially. So one of them's vertical, one of them, so we have a cut across like this, and that's one of the gratings. Turns out that has some problems too, because we get a repetition pattern between these two, and that gives beatings in the Fourier domain. The details really aren't important, but what we found is by far the best is taking these gratings and putting them in a special spiral. So along any one of these lines, if you take a cut across it, it is a phase anti-symmetric grating. But when you're way close to the center, we use fewer degrees of freedom, fewer, we call them W's, are the parameters that tell us the width of these things. So we can have lots of structure way out here because we have all the space on the PicoCam. Way down here, we only have a few, so we make them similar. So this is sort of the core general spiral anti-symmetric phase grating that's going to be the heart of our PicoCam, and it stores the 2D Fourier information, which we can show empirically and mathematically. So overall, from beginning to end, here is a particular phase grating where the gray might be high and the white might be low. And the point spread function, that is to say, if you take a star or something that's infinitely far away and it's sending a plane wave through this phase grating, here's what the signal would be on the sensor. This pixel would be bright, this would get nothing, and so forth, all the way like this. This is a point spread function, and it's unlike point spread functions that people have been using for many, many years. It's a very unusual point spread function, but it contains all the Fourier components, as I'll show you in a slide in about 5 or 6. That means we can recompute or compute the image. So if you have a source object, lights, so this is sitting in front of the PicoCam, so light's coming from this, through the PicoCam, and so forth. And now we want to know what the signals are on the sensor. Basically, we do a convolution. It's not exactly a convolution because there's a slight angle dependence. But here is what the signals look like on the sensor. It's a mess. It looks like a blob. And if you sit down and really think about this, this is amazing. This blob, this mess, contains all the information in here. And you just have to compute it. It's just not it's not an image for humans. It's an image for machines, an image for algorithms. And so you can then take that and take the information and compute the image. So from this, using some algorithms that I'll show in a few slides, we can recompute the image. We can think of this as a linear transformation that we have an X is our source, and then we have a linear matrix H that gives us an output Y. Here's our Y. And now we want to, it's a linear process. So we could say that the output Y is A, or H, times X, plus some noise. There's going to be some noise in the sensors here. We put in 1% noise, for instance. Or there is 1% noise, shot noise, and other noise in the actual sensor. And then we want to reconstruct the image by inverting the matrix using what's called Tikhonov regularization. I'll come.
Is this a single point sensor?
No, we have, this one happens to be, I think this one's 40 across, or 50 across, and 50 down. You count these things, 1, 2, 3, 4, 5, whatever this is. This is the grid. And we can make these things larger or smaller based on our needs. For the algorithmists in the audience, I have a better slide on that. No, it's a real matrix. This is a real light comes in. You give me a real value of light here, comes through here, and we get a real value there. It's real light. Just to compare our reconstructed image for one of our smaller PicoCams with that came from the planar Fourier capture array, it's certainly much better. Also, ours is 1/37th the area of this. So it's getting a better image with a smaller area. So here is the, the way you use a Moore-Penrose pseudo-inverse, you take that transformation matrix H transpose H plus a regularization. This is the identity matrix. Take the inverse of that. And then you construct this matrix times whatever output vector you have, the vector of values on the output. And it's somewhat compute intensive. It can be highly parallelized, but that image you just saw, it's 350 million multiply accumulates. So you don't want to put that at the sensor. You want to put the computation somewhere else. You want to sense it, send those signals, those small number of signals, back to the compute, and that's where you do it. And for almost every application I can think of, you don't need the image at the sensor. You need the image somewhere else. You're putting this in an endoscope, and you're putting it in someone's ear or nose or whatever it is, and then the doctor is looking at a screen. You can do your compute right here. Who cares getting the image there? So separating the compute from the sensing gives you all this design freedom to make very, very small imagers. Now, one of the benefits of PicoCam imagers is the following. It involves depth of field. Now, those of you in basic optics are familiar with the problem of focusing and depth of field. If we have a converging lens, standard camera lens like, and we have a point here, it sends out rays that I've arranged to be in perfect focus. We get a nice sharp image of the dot on the film or the CMOS image sensor, or CCD array. But for an object that's further away, by the laws of optics, that is brought to a focus closer, and hence the rays spread out. We get what's called a blur spot here. It's a blurry image. This is in focus, this is not. And likewise, for an object that's close, the rays don't cross or don't come to a point, and they're going to be out of focus too. And so you've seen images like this, where an object in the intermediate distance is in nice sharp focus, something close is blurry, something far away is blurry as well. This is limited depth of field or depth of focus. Well, another way of looking at that or understanding that is the following. Take our point here, and we can think of the wave fronts that are emanating from that point and looking at the curvature of the wavefront as it hits the lens. Here it has this particular curvature. And for an object here, it has a rather different curvature. It's the difference in the curvature of the wavefronts that means that we have limited depth of field, that the one will be in focus and the other not. Well, for a PicoCam imager, the aperture is so small, say 10, 20, 30 microns, that if you're 100 microns away, you start getting a wavefront that's almost planar. In other words, we call it the far field. When you have something small, the far field, optical far field, might be a millimeter away, and so is something infinitely far away. So we can get a depth of field between, say, 1 millimeter, that'll be in focus, we'll get a good image from that, and something infinitely far away. This is an enormous depth of field. Corresponds to 1,000 diopters in that particular case. So objects are going to be sharp here, 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 all the way back to infinity, the mountain in the distance. So let me summarize some of these things here. We have this integrated diffractive optics. I haven't talked about the packaging, how you mount these things and make sure they're co-aligned. Those are sort of engineering details I don't need to go into right now. But we mount this, we manufacture this separately, then mount it onto the CMOS image sensors. And the sort of design flow that should be in your mind as you fall off to sleep tonight is if you have an input like this and pass it through the optical or PicoCam spiral odd symmetry phase grading, we get this mess of signals, but then we can recompute the image. So, quick question.
How many bits do you need to represent that?
We usually use 10 bits. This is a standard, for the experiments I'm going to talk about, we just use standard CMOS image sensor, an Aptina sensor that we buy off the shelf, and then do all our mounting on top of it. So you can do more or less, but we usually use 10 bits now. So here's our experimental setup. We have a PC. We have a commercial sensor, an Aptina sensor. We use that because it has some good optical properties, but also you can easily read off individual pixels on the sensor. And then we have a screen that's going to present our patterns. And here, I hope you can see it. It's hard to see from here, but you're seeing this better. Instead of making a single PicoCam, we made 40 different experiments all on one big grating, one that covers the image sensor. So this is, bar is 200 microns. So this is almost 5 millimeters and 4 millimeters, something like this. And we have 40 different experiments. So the gratings, everything I told you about, came from this experiment, that little teeny one. There's our scanning electron micrograph of the phase grating. And we also, I'll come back to it, tile gratings, how you can pack them. That turns out to be one of the other benefits of spirals, that you can pack them into an array. If you have to fill an area with spirals, you can do it better than if you do these pinwheels and other shapes, but I'll come back to that. So here are our phase gratings. And here's micrographs, I hope you can see them, of the phase gratings. They look really quite nice, nice and sharp. And you see the spirals here. And this one is one of these packed arrays that I'll come back to why we want to use those. Here's from the side, just to show the quality of the kind of phase grating that we can produce. Now here's the point spread function of that experiment, J3b. Don't worry about the number. So if we have light from a point source far away, here's the pattern. This is the point spread function, the pattern of light on the sensor. And again, it's unusual. You know, you didn't learn this in Optics 101 to get something like this. When you have a standard lens, you'll get what's called an airy disk, a very clear mathematical form. This has some very complicated properties. And we can have wide field of view. We can, here's the point spread function for 2 points, 21 angular degrees apart. We can still get them on the sensor. And we could make it even wider. It depends upon the thickness of the grating, and the details aren't really important, but we can get point spread functions that look something like this. And if you have adjacent point spread functions, they differ enough. So here on our display screen, we have basically a point. We illuminate it from a point, one of the pixels on the display screen, the input screen, and then the next one, and they give us 2 different point spread functions. But we can take the difference, and you can see there's structure here, enough information to tell that there's a difference so that we're capturing information at that resolution. It's very difficult with many lens systems when you have something out of focus. The blur of one overlaps the blur of the other, and it's difficult to see the difference. So the details are discernible. Now, I've told you that we're capturing all the Fourier components, but haven't really proven it. Well, you can take that point spread function and do a Fourier transform of it in order to find out what different spatial frequencies pass through are captured by that spiral. And here's a plot of it. I hope you can see. So this is a horizontal spatial frequency, bars per degree, getting higher and higher as you go on, and likewise vertically. And what you get is something that fills in a great deal all the way out to roughly the Nyquist limit, the highest spatial frequency that the sensor itself could ever possibly pick up. But we don't see holes in it. We don't see zeros. That's the worst thing you can get in a linear system like this. If there happened to be a 0 here, instead of being yellow, this happened to be dark blue, somewhere like this, that would mean there's a spatial frequency, in particular orientation and spatial frequency, that if in the world was present in the world and passed through the system, the PicoCam could not detect it. It just doesn't even exist for the PicoCam sensor. And then you will never be able to reconstruct it, of course. So this shows that we're capturing, we don't have zeros in the Fourier domain, which is really crucial. This is a detail that involves the fact that we use square pixels. I won't go into that. It doesn't really matter. Now, for those of you who work in linear algebra and this matrix inversion, this Moore-Penrose pseudo-inverse, know that the ideal, or the simplest, is if that matrix H happened to be the identity matrix, 1, 1, 1, 1, 1, 1, 1, 1, 1. Then it's easily inverted, and whatever you get as your output, you know what the input is. And that identity matrix has equal eigenvalues all the way through. All its eigenvectors have the same magnitude. Well, the eigenvalues for our matrix H due to the spiral PicoCam are not all the same. This is not the identity matrix by any means. And so here's a graph of the magnitude of the eigenvalues, or the eigenvalues themselves, as ordered by the magnitude, something like this. And depending upon the overall noise level, there are only, if you have no noise, you can reconstruct the image very, very well. But if you have some noise, you might lose information from some of the higher eigenvectors. And here's a plot of the handful of these eigenvectors. Here's one of the low ones. This is basically the DC, how many photons get through. And that has a very high eigenvalue. In other words, if we know how many photons, how much light is getting to the PicoCam, no matter what the scrambling is, we can count those at the very end. That's an eigenvector, and we can capture that very, very well. Other vectors are not quite as good, and so forth, all the way down like this. So part of our design of that spiral is to do this eigenvector analysis of the transfer function H, or H transpose H, and we want to make this as flat as we can. And this is one good one, and we might be able to optimize that by changing those W's, those parameters on the phase grading. So here's some of our value propositions, why the world should care about this. They're very small. They'll keep getting smaller as time goes on, mainly because we can get smaller pixels, and the support circuitry, the power, the I/O, and stuff like that keeps getting smaller. It's very, very thin. It's only 15 to 20, or maybe a little bit more microns on top of say a 500 micron thick wafer. Very low mass. These things are light as a feather, or much less heavy than a feather. They're very inexpensive, roughly 15 cents for the sensor part alone, just the grading on top of the CMOS. But with the computation, that of course adds cost. Can be integrated with CMOS. So if you've got a chip that does some processing, but you want to have a camera on it, well, don't necessarily put a lens on top of it. Just put a PicoCam grading and some processing somewhere in order to get your camera. And I don't have time to talk about it, but we've arranged the PicoCam's pixels in a square grid. There's no requirement that we do that. We could make those pixels all in a line, for instance, just so long as we have the proper gradings over top of them. So we could make what we call needle cam. We could take something that's very, very thin and put a pixel sensor here, 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 all the way along it, and different gradings over top of it. And this can be really, really thin so that you can put it through the hole of a hypodermic needle or something like this. Now, the image analysis is really tricky problem then, because when you put it through, you're not capturing a real picture of the whole thing. You have to sweep the whole thing through and know what was aligned with what at a certain time, maybe with a fiducial mark or something like that, and then compute the image. So there's a lot of compute. So there's this sort of trade-off. You can make things really small. This PicoCam, this needle cam, we think we can make 20 of them fit through the hole of a hypodermic needle. But to get the image, you're going to need a couple of FPGAs, maybe a couple of real compute power. That's the world of computational imaging, looking at the optics and the signal processing both together. But I think the greatest value in all PicoCam work is that we can make these sensors application specific. That is to say, we can choose a grading and the processing to solve a particular problem. Not necessarily make an image. We might want an image in some certain cases, but you might just want to detect visual motion. Take a teeny thing the size of a pinhead and put it somewhere in a room or wherever on your clothes, whatever it might be, and have it respond if there's just any change in the visual field. That's going to be very easy to compute. You just take the Fourier, you take the signals and look for any change by K%, whatever it might be. You don't have to do all that matrix inversion and stuff like that. And things like a barcode reader. If you know that your barcode is vertical, and you also, of course, know that it's binary, that is, say, black and white, you can make your gradings be vertical and have proper, capture all the horizontal spatial frequencies. and then do your processing, not to get an image, necessarily an image of the grating, but to read it and get a code. So there's a lot of work to be done here. Some applications will work well, some may not, and that's what research is all about. One of the other benefits is that PicoCam can use small pixel pitch sensors. Now, those of you who have taken the course on computational optics here, or optics, know that there's a what's called the diffraction limit of an imaging system. If you have a lens of a given size, really it's the F number, there's a resolution, there's a spot size, the Airy disk, the smallest resolution that you can possibly get through that system based on the wave nature of light. And if you go through it for typical cameras, point and shoot cameras and stuff like that, that size is roughly 2 microns, 2 micron pixel. And image sensor makers and camera makers made their sensors down to 2 microns. For advertising reasons, and almost entirely advertising reason, they kept making more of them. Oh, you've got a 12 megapixel camera, I've got a 14 megapixel, I've got a 60. You're not getting more information. By the laws of physics, you're not getting better images through those. So I could give you a 1,000,000 megapixel camera, and you're not going to do that much better than, say, a 16 megapixel camera. And so this led to what's called the megapixel wars, and it was just advertising hype, and the optics experts saw right through it. But one of the nice things about PicoCam, which involves the numerical aperture, I won't go through it, it's basically the F number for the PicoCam, allows us to use smaller pixel pitch sensors, down to about a 0.5 micron. And sensor manufacturers know how to make them that small, but they stopped making them because they said, the jig is up, this megapixel war is over, and nobody's buying these ones with more and more. But we can make use of them. We give them a reason for making them smaller. Actually, let me skip on this. So there's some challenges. There are a lot of, this is still research, a lot of problems. Some applications require more computation than traditional sensors. Imaging certainly does, as we pointed out. For some applications, the sensor data must be processed and converted into traditional formats. Even if you get an image, then you've got to do things like put it in JPEG if you're going to do other kinds of processing. It's only moderate low light sensitivity. In fact, it's because of its numerical aperture, or its F number, it actually is pretty sensitive for an imager this small. But because it is this small, we're just not getting that much light. So this will work in a room. PicoCams work, we've demonstrated in rooms like this. But at night or low light levels, we just don't get the photons. We don't have this signal. And there's no way around that. Even you can try and integrate for a long time, but it's still, when you have a small sensor, you're just not getting the signal. Everything I've talked about up to now has been lensless imaging. Now, you can also use these gratings with a lens. Now, everything I'll show you from here on is simulation and analysis. We haven't built one of these things, but I want to show you some of the benefits of lensed PicoCams. So here's one of the gratings. Imagine we have a primary lens, like a camera lens, and have a phase, a PicoCam grating, a phase antisymmetric grating that has been tiled so that we cover the sensor array here. Now I've separated them just for geometry, so you can see the geometry. Imagine I have a cylinder of light coming in, and I'm going to change the aperture, the radius of that. That will sort of sweep out the pattern through the spiral phase grating, and so the point spread function will look something like what we saw before. But it will depend upon the distance to the object. So let me remind you of this. I showed you before this depth of field problem. Here's a standard lens. If we have a close object, the rays don't come together. It's spread out. We get this blur spot. But when you have the same setup and now pass the information through a PicoCam grating, you get something that looks like this. And this contains a lot more information. It's a sort of a visual chirp and contains more information in the Fourier domain than does this. Or another way to think about it is with a standard lens that's out of focus. If you have a blur spot for one star, say, and then another star, they overlap a great deal, and it's difficult computationally to resolve them. but if you have these, the images, well, really the point spread functions, it's much easier to distinguish the red, the position due to of the star due to the red one and to the green one. That involves, you can look at this in the Fourier domain. The main thing is, since this process involves dividing by the Fourier transform of the point spread function, if you have zeros in the point spread function, you have real problems. And our spiral gratings do not have zeros in the point spread function, in the Fourier transform of the point spread function. So here, if you just have a lens system under certain circumstances, certain conditions of defocus and so forth, looking at these letters, it's very difficult to read them, even if you sharpen them using what's called Wiener filtering. But if you use our spiral phase grading, it's this sort of visual chirp that leaves more of the Fourier information, and so you can read it somewhat better than. So here is another way of looking at it. Here is a PicoCam grading, and imagine we have a point source, there's a lens up here, and we're moving the position of a point source so that the rays are coming at different angles. And here would be the point spread function on the sensor, and this is the Fourier transform of this function. And here it is without the PicoCam grading, without this spiral, and you get something like this. What you notice, it's probably hard to see, it's certainly hard to hear, but for this one, there are more regions of true zeros in the Fourier transform. And when you have zeros in something like this, you get poorer reconstruction, and that's why you couldn't read those words with the lens we saw a moment ago. Now, under certain circumstances, you can use a lens system with a PicoCam grading in order to infer depth. So this is all simulation, but it's a realistic simulation. We simulate a scene that has something close, an ice cream cone, and something far away, the Leaning Tower of Pisa. And for a standard lens system, they have different point spread functions. That is to say, one's better focused than the other, and so we have different blur spots, different point spread functions here. And so the image you get would be a blurry ice cream cone and a blurry Leaning Tower of Pisa. And you can sharpen this, basically the inverse of this function, and you can sharpen it and get a better image of the ice cream cone and of the Leaning Tower of Pisa. Well, you can also do this with a PicoCam grading, and so because of the geometry and that diagram I just showed you, the point spread function for something close will be 1, and for something far away will be something else. And these are different enough that we can search through the, computationally search through the inverses in order to get the best reconstruction at any point. And so this would be the image comparable to this, a blurry image. It's slightly different from this one if you look really closely, but it's still blurry and hard to see. But if you go through, you can, using the inversion from those point spread functions, you get a much better image. I hope you can see it here. I'll show it on the next slide. That it's sharper here, and it'll be sharper than those. Let me show you on this. So this is with just the disk-like point spread function, the lens, and here it is with the spiral phase grading. I hope you can see that there's less noise here. It's much sharper. And if you look at the person standing on the tower, it's very difficult to see in the lens system, but with the PicoCam system, you can see it somewhat better. And here's the photograph, so it's clearly better. But because we swept through those different inversions, we can find which one is best using error measures, and get, hence, a depth map. This object was close, this object was far away. So it's a very simple depth map in a lens system with a PicoCam. For the real optics experts around here, the grading can help you correct for aberrations. Even if you design your lens as well as you can, it won't give you a perfect image. We have Petzval aberrations, the chromatic aberration, curvature of field. There are a whole number of imperfections, if you will, in the images. But putting the light passing through the PicoCam grading preserves the Fourier components better so that you can computationally sharpen the image and get a better image overall. Now, some of you are familiar with what's called coded aperture imaging, and we're related in some ways, but in coded aperture imaging, you take a coded aperture, just a plate with special holes in it and put it behind the lens, and what you capture here contains certain information but not others. We're related to that. That allows only light in a certain place, but the point spread function becomes a scaled image of the coded aperture, but you're throwing away a lot of light, and we don't throw away light in PicoCam. Planoptic imagers, where you have a main lens and a lenslet array to get a set of pixels down here, allows you to do computational refocusing. So when, the planoptic cameras have resolution intermediate between the micro lens pitch, the pitch due to this, and the pitch of the sensor pitch. And you have a limited numerical aperture for the micro lenses, and you have some other problems. It has some great benefits, but we're somewhat related to that. But there's no free lunch. There are ways to sort of fool a PicoCam that you can have very unusual patterns that can fool the PicoCam algorithm, if you will, into thinking that that ice cream cone was really further away, but of a different shape. We're just starting doing the analysis of that, but just on a degree of freedom analysis, we know that you can't be perfect on that, and there's a lot of work to be done. So in summary, I've introduced these spiral phase anti-symmetric gratings for ultra-miniature lensless cameras. They give you good resolution for the pixel pitch, and they have much better depth of field than traditional cameras. You get this very, very large depth of field. And it has better resolution and low light performance than, turns out, planoptic cameras, and has a different notion of how you refocus the final image. So with that, I will thank you for your attention. Thank you.